When we talk about the cloud or AI, we use language that makes it all sound completely weightless.
Right, yeah, like it's just floating up there.
Exactly. We're basically conditioned to think it's just algorithms.
Right.
Just data floating in the ether, infinite software. You type a prompt, and by magic, an answer just appears.
Which is a very intentional illusion, by the way. I mean, the tech industry has spent the last 2 decades kind of abstracting away the physical world.
But software still has to run on hardware.
It does. And right now, that infinite software demand is, well, it's slamming into finite physical reality.
Which is exactly our mission for today. Welcome to the Deep Dive. We are exploring the massive physical wall the AI revolution is hitting at full speed.
Yeah, we're looking at a $1 trillion traffic jam, basically.
Right, and to show you why the entire industry is stuck in this jam and how it's reshaping global supply chains, we've synthesized a really fascinating stack of sources for you.
Some heavy hitters in there, too?
Definitely. We've got Wall Street financial reports from Goldman Sachs and Morgan Stanley, some breaking industry news out of South Korea, and a really detailed technical analysis on the physical world underneath AI.
And the goal here is to give you a shortcut to understanding these invisible physical miracles happening behind your screen right now.
Because these aren't just abstract engineering problems anymore.
No, not at all. They're dictating the movements of the largest companies and the deepest pools of capital on Earth.
So a perfect starting point for this is some breaking news involving NVIDIA CEO Jensen Huang. He recently took a trip to South Korea.
Right, a highly publicized trip.
Yeah, and according to the reports, he met with SK Group Chairman Chae Tai-wan and SK Hynix CEO Kwak No-jung. But, and this is the crazy part, they didn't meet in some sterile corporate boardroom.
No, they went out for kimak.
Right. Korean fried chicken and beer. At a casual Kanbu chicken restaurant right in the middle of Seoul.
So, okay, let's unpack this. Why is the leader of the world's most valuable semiconductor company hammering out multi-billion-dollar supply chain strategies over, like, a basket of fried chicken?
Well, if we connect this to the bigger picture,
Yeah.
you really have to look at the specific hardware SK Hynix manufactures.
They're memory chips, right?
Exactly. SK Hynix DRAM is the foundational memory slated to power NVIDIA's upcoming Vera data center CPU.
And the Vera is a huge deal for NVIDIA.
It's an incredibly high-stakes project. It's their inaugural standalone CPU designed specifically for data centers. So it pulls them out of just the graphics card space,
Right, making them a direct, aggressive rival to Intel's Xeon and AMD's EPYC processors.
Yeah, and NVIDIA absolutely needs SK Hynix's memory to make that Vera launch successful.
But reading through the accounts of this dinner, Huang didn't just fly halfway across the world to celebrate a partnership.
No, it was actually a warning. Yeah, he used this casual setting to deliver a really stark warning to the whole industry. He basically stated bluntly that the severe memory shortage we're seeing is going to persist for several years.
Not months.
Years.
Right, because market demand from cloud providers trying to build out AI infrastructures has just completely broken the supply chain's physical capabilities.
And that timeline is what totally shocked the market. I mean, historically, memory goes through these highly predictable boom and bust cycles.
Like they overbuild, the market floods, prices drop, they pause factories.
Exactly, and then prices rise again.
Yeah.
But the kind of memory required for AI isn't your standard memory.
It's different.
Very different. It's a highly specialized architecture called high bandwidth memory, or HBM. And the physical reality of how HBM is manufactured is the root cause of this massive bottleneck.
I was looking at the notes in our sources on the actual manufacturing process for HBM, and it is just mind-blowing. They aren't just printing a flat chip on a silicon wafer.
No, they're vertically stacking DRAM dies, kind of like a microscopic skyscraper. And to make that work, they have to shave each individual silicon die down to 30 microns thick.
Right.
For context, a standard human hair is about 70 microns thick. So they're taking a brittle piece of silicon, shaving it down to less than half the thickness of a human hair, and then stacking 8 or 12 of them on top of each other.
And when you get silicon that thin, it becomes incredibly fragile. I mean, almost translucent.
Wow.
Yeah, and you have to perfectly align these microscopic pathways, they're called, through silicon vias, straight down through all 12 layers.
So the electricity can actually flow from the top floor of that skyscraper to the bottom.
Without short-circuiting. And here's the kicker. If a single microscopic layer in that stack is misaligned by a fraction of a millimeter.
Or has, like, a single speck of dust on it.
Exactly. You can't just fix that one layer. The entire stack is ruined. It goes straight in the trash.
Oh, man. So because of that complexity, the manufacturing yield has to be a nightmare.
It's brutal.
The reports note that manufacturing HBM requires 3 to 4 times the wafer capacity of standard memory chips. So is this basically like bulldozing 4 standard apartment buildings just to build one luxury penthouse? It essentially cannibalizes the regular housing market?
That is a brilliant way to conceptualize it, yes. HBM is incredibly resource intensive, both in raw silicon and in time.
Right.
And because of this, it is physically locking up about 30% of the monthly clean room capacity of the major memory manufacturers globally.
And a clean room is that ultra-sterile environment where the chips are made.
Exactly, and there's a hard physical limit on how much clean room floor space actually exists in the world.
So every square foot dedicated to stacking HBM for AI
Is a square foot that isn't making conventional memory for your laptop, your smartphone, or standard servers. HBM is literally cannibalizing the regular DRAM supply.
And the real-world consequence of this cannibalization is staggering. I saw a projection from KeyBank Analysis in our stack regarding NVIDIA's upcoming Rubin GPU.
The Rubin is their next-generation flagship chip.
Right, and KeyBank projects that actual production volumes for the Rubin are going to settle near 1.5 million chips for the year, which is a massive 25% decrease from NVIDIA's original goal of 2 million units.
And that isn't because of weak demand.
No, it's a 25% cut purely because SK Hynix and Micron physically cannot supply enough high bandwidth memory to put on the chips.
NVIDIA has practically infinite demand, but they're entirely tethered to the physical output of these factories.
Right.
And when physical supply is this severely constrained, but software demand is seemingly infinite, the entire balance of power shifts.
The companies making these chips are suddenly holding all the cards.
Exactly. And the financial institutions are waking up to this new reality. We are seeing a complete paradigm shift on Wall Street regarding how these infrastructure companies are valued.
Yeah, looking at the financial analysis from Goldman Sachs, Morgan Stanley, and JP Morgan, they're all essentially signing the death certificate for the traditional memory cycle.
Declaring the boom and bust era officially over.
Right. Because hyperscale cloud providers like Microsoft, Google, Amazon, they're terrified of falling behind in the AI race. So they're locking in long-term agreements or LTAs.
With massive cash prepayments just to guarantee their place in line for memory.
So those prepayments fundamentally alter the business model, don't they?
Totally. It transforms companies like SK Hynix and Samsung from cyclical commodity businesses into highly predictable AI infrastructure assets.
Which changes how Wall Street values them.
Right. Historically, Wall Street valued memory companies using a price-to-book multiple.
Which is a metric for heavy industry, right?
Yeah, it essentially asks, if we sold all your factory equipment, your steel, your concrete for scrap, what's it worth?
Right.
But now, because of these guaranteed multi-year contracts, the big banks are shifting their models to a price-to-earnings multiple.
The metric used for high-growth tech companies.
Exactly.
Yeah.
Valuing them based on guaranteed future cash flow.
Okay, so what does this all mean, like, for the average investor watching the market?
Well, it means institutional investors are hunting for backdoor ways to play this exact physical shortage.
Oh, like the iShares MSCI South Korea ETF.
Yes, ticker EWY. On paper, this looks like an incredibly boring, plain vanilla, single country fund.
Because historically, South Korean equities trade at a discount, right? The famous Korea discount.
Yeah, due to geopolitical risks, complex corporate governance, things like that. You'd assume buying this ETF just gives you broad, sluggish exposure to Korean banks, shipbuilders, automakers.
But reading the prospectus, underneath the hood, it's secretly a high-octane AI hardware trade.
Completely. Nearly half of that entire national fund is concentrated in just 2 companies.
Samsung and SK Hynix.
Bingo. Because those 2 companies essentially operate a duopoly over the HBM market, this quote-unquote boring country ETF surged 80% year-to-date.
Wow. 80%.
Yeah, Wall Street is using it as a stealth vehicle to ride the HBM bottleneck.
But memory is just the first hurdle, isn't it? I mean, even if SK Hynix magically tripled their cleanroom capacity to 0 and produced all the memory NVIDIA needed,
we would immediately hit another physical wall in the assembly process.
right, because modern AI processors are not single chips.
No, the industry has moved to a chiplet model.
Which means the main processor, the high bandwidth memory we just talked about, and the input-output controllers are all manufactured separately. And then they have to be physically stitched together.
Stitched together on an advanced substrate, yeah. So they can communicate instantaneously and act as a single unified brain.
And the dominant technology for this microscopic integration is called CoWES, right?
Yeah, CoWES, chip on wafer on substrate. And this highly specialized packaging is handled almost entirely by one company.
TSMC in Taiwan.
Exactly.
The sources basically describe TSMC's CoWES packaging as the ultimate toll booth for the AI revolution.
It really is. You cannot sell a finished AI chip if it isn't packaged.
And TSMC is the only game in town operating at the required scale.
But they are completely sold out of this capacity deep into 2026.
2026? That is wild.
Yeah. They're desperately trying to ramp up production, aiming for around 120,000 CoWES wafers a month. But customer demand is doubling annually.
So the gap between what the market wants to buy and what TSMC can physically package is just widening every single quarter.
It is. Which raises an important question, right? How do you connect all these highly advanced packaged chips once they actually make it into a data center?
Ah, the networking side.
Exactly. Inside an AI training cluster, you aren't just plugging in a handful of computers. You're networking tens of thousands of GPUs together.
And traditionally, those connections use high-speed copper cables.
Right. But the industry is hitting the physical limits of what copper can do.
Yeah, because at the terabit per second speeds required for modern AI, copper physically degrades the electrical signal over distance.
Signal loss or attenuation.
Right. I like to think of it like trying to blast a fire hose of water through a really dense sponge.
Oh, that's a good visual.
Yeah, the further the water has to go through the sponge, the more pressure you lose. So to boost the electrical signal through copper, you have to pump in a massive amount of power.
And the cables themselves become so thick, heavy, and rigid that you physically cannot fit enough of them into the server racks.
So what's fascinating here is how the industry is solving the copper problem. They are abandoning it entirely and moving to light.
It's a massive transition.
To a technology called co-packaged optics, or CPO.
Right. Instead of forcing an electrical signal through a thick copper wire, or even using a traditional optical transceiver plugged into the front of a server,
CPO integrates microscopic optical engines directly onto the switch package itself.
mere millimeters away from the main silicon chip.
Wait, so the electrical signal only travels a microscopic distance before it's instantly converted into a laser beam and shot through a fiber optic cable?
Precisely. It's like replacing that dense sponge with an empty, frictionless tube.
That is incredible, and the performance jump is staggering, right?
Oh, massive. Signal loss drops from 22 decibels with copper down to just 4 decibels with light.
And even more critically, the power consumption required to push that data drops from roughly 30 watts per port down to just 9 watts.
Which is huge. When you multiply that 21-watt saving across an AI cluster with, say, 2.4 million individual networking links.
You are saving tens of millions of dollars a year in electricity just on the wiring alone.
Exactly.
But okay, here's where it gets really interesting. I get that using lasers saves power on the networking side. But looking at the total power draw of the AI chips themselves, they are pulling unprecedented amounts of electricity.
Yes, they are.
Even with efficient wiring, aren't these massive clusters going to generate so much raw heat that it literally melts the server racks?
Well, the heat problem is the most immediate, visceral, physical constraint operating inside these data centers right now.
How bad is it?
To put the numbers in perspective, a standard data center rack a couple of years ago used about 15 kilowatts of power. NVIDIA's upcoming Kyber rack, which packs 576 GPUs into a single vertical tower, it will pull a staggering 600 kilowatts.
600 kilowatts in a single rack. Just to contextualize that scale for a second for you listening, that is enough electricity to power roughly 500 average homes.
Yes.
And they are squeezing all of that energy into a metal box the size of a standard kitchen refrigerator.
And at that extreme density, air cooling is physically dead.
You just can't fan it away?
No amount of industrial fans or cold air circulation can remove that volume of heat fast enough to stop the silicon from turning into slag.
So they have to pivot.
The industry has been forced to pivot abruptly to direct-to-chip liquid cooling.
Because liquid is far denser than air and can absorb heat much more efficiently.
Right. But bringing water into a data center introduces an entirely new, terrifying set of supply chain bottlenecks.
I mean, you're suddenly piping millions of gallons of liquid coolant directly over tens of millions of dollars of incredibly sensitive electronics.
A single drop of water in the wrong place is catastrophic.
So how do they prevent that?
It creates extreme life-or-death dependencies on seemingly mundane components. For example, if a technician needs to service a server blade, they have to unplug the liquid cooling tubes without spilling anything.
So they need highly specialized, quick disconnect fittings.
Exactly. And a Danish engineering company named Danfoss currently holds a near monopoly on these specific leak-proof valves for AI data centers.
Wow, and near monopoly on valves.
Yeah, it's a relatively tiny, inexpensive metal part, but the switching cost is astronomical because if a competitor's valve leaks even a drop, it could short out a $200,000 server instantly.
That's terrifying. And the power delivery itself to run a 600 kilowatt rack is also a complete architectural nightmare, right?
Oh, absolutely.
The analysis points out that if you try to deliver 600 kilowatts of power using the standard 54-volt architecture that data centers have used for decades,
The copper bus bars inside the rack would weigh 200 kilograms.
that is over 400 pounds of solid copper shoved into a single rack just to physically deliver the electricity.
It's too heavy, it's too expensive, and it takes up space needed for compute.
Which is why the infrastructure layer is being forced into a voltage revolution.
Right. To avoid using 400 pounds of copper per rack, the entire industry is shifting to an 800-volt DC architecture.
Which relies on the exact same underlying physics that revolutionized the electric vehicle industry.
Exactly. Because power equals voltage multiplied by current.
So if you dramatically increase the voltage, pushing the electricity jumping up to 800 volts, you require significantly less current to deliver the same total amount of power.
And current is what dictates the thickness of your cables.
Right.
Lower current means you can use vastly thinner wires, which reduces your copper requirement by nearly half and drastically cuts down on the heat generated by the cables themselves.
But you can't just plug standard servers into an 800-volt grid, can you?
No, standard silicon components would literally melt or arc electricity at those voltages. This shift requires completely redesigning the electrical infrastructure.
So new hardware all around.
Data centers need new solid-state transformers. They need advanced semiconductors made of gallium nitride.
Which has a wider band gap than silicon, right? So it can handle massive voltages without failing.
Exactly. And they need entirely new safety protocols for the human technicians working anywhere near these racks.
It really paints an incredible, almost overwhelming picture of human engineering.
It really does.
The next time you use a generative AI tool to draft a quick email or summarize a PDF or generate a funny image, just take a second to think about the physical reality of what you are actually doing.
You aren't just pinging weightless software in the cloud.
No. You are triggering a cascade of hidden physical miracles.
You're relying on microscopic layers of thin silicon stacked perfectly together in a pristine clean room.
You're firing lasers across optical engines to avoid signal degradation.
You're pumping liquid coolant through monopolized leak-proof valves to stop 600 kilowatts of electricity from incinerating the circuit boards.
And you are depending on an 800-volt gallium nitride power grid to feed the whole system.
We started this deep dive talking about a trillion-dollar traffic jam. The software wants to run infinitely, it wants to eat the world, but it is fundamentally bound by the limits of packaging, heat, and power.
And the companies doing the heavy lifting to solve these physical problems, the ones stacking the memory, manufacturing the cooling valves, integrating the optics, they're quietly building the true infrastructure layer of this decade's biggest technology transition.
It's a massive, incredibly dense physical wall, and the reality is we are only just starting to climb it.
Which leaves us with one final lingering question to explore on your own.
What's that?
If this current generation of artificial intelligence requires us to entirely rebuild our physical infrastructure from the ground up, tearing up copper wires, replacing them with lasers, hoarding clean room space, and completely redesigning our power grids and cooling systems, what happens when the next generation of AI demands 10 times as much compute?
Man.
Are we frantically building an incredibly expensive physical world that will be obsolete before the concrete even dries?
That is the multi-trillion-dollar question right there.
Something to keep in mind the next time you type a prompt and wait for the magic to happen. Thanks for joining us on this deep dive.